Hi guys, today we're going to be learning about percent yield and limiting reactants. So this is unit 7.5 and we'll start off talking about percent yield. So an easy way to explain percent yield is just even thinking about a test score. So suppose a student had to take a test worth 60 points, so the maximum they could get is 60. But let's say they didn't do so hot, got 30. Then their percent score is 30 over 60 times 100. And so if we think about how an equation would be written, it would be the actual score over the theoretical score times 100. And so this is the same idea for percent yield, but instead we typically talk about it in mass. So we're going to have an actual yield over some theoretical yield and then we times it by 100 to get our percent yield. So for example, if we're thinking of mass of a product, like how much we're going to make, ideally your percent yield should never be greater than 100 because that means you have more than you should have made. But usually it is less than 100% due to a lot of factors. And so some of these include if the reaction doesn't go to completion, as if it doesn't finish reacting, well, then you're not going to form everything you could. Sometimes if you have impure reactants or competing side reactions, then you're not going to get 100% either. Another one, which is common for us in lab, is loss of product. And this can be due from filtration, transfer, things getting stuck to the scupula, etc. And lastly, careless measurement. Because if you don't have the right measurement, you're going to throw off your percent yield calculation. And so let's start off with an example. Theoretically, we should make 300 grams of a product, but we only get 213 grams. What's the percent yield? So remember, we're doing an actual over theoretical times 100. So what we get is 213 over 300 times 100, and we get 71.00% yield. So these aren't too bad. And so we also need to be able to calculate one of the values. So calculate the actual amount or the theoretical amount if we were given already our percent yield. And so this is just basic algebra. We're just rearranging equations. So in this problem, it says if we have a percent yield of 75% and we have a theoretical yield, what's the actual? And so if we set up the equation, percent yield is equal to actual over theoretical times 100. What are we solving for? And so we're solving for the actual yield. And so we just have to do some changing and rearranging. So this is just like when we worked with the gas laws. If we pretend this percent yield is in the numerator and we have a 1 in the denominator, we're going to be moving this 100 to the denominator. Theoretical is in the denominator, so we move that to the numerator. And so our new arranged equation is percent yield times theoretical all over 100 is equal to our actual. And so if we were to use our numbers, we then have 75% times 18 grams all divided by 100. And that gives us an answer of 13. This is technically units of percent, but anyway, gives us an answer of 13.5 grams. So this would be our actual amount. All right, and so stoichiometry is not going away. This is a huge part of this unit. And so sometimes you need it to solve for percent yield. So let's practice with an example. if we have the reaction, lithium hydroxide with potassium chloride goes to lithium chloride and potassium hydroxide. If we know that this equation uses 20 grams of lithium hydroxide and we have excess of potassium chloride, how much lithium chloride could theoretically be made? After doing the experiment, the reaction produced 6 grams of lithium chloride. What's the percent yield? So this is kind of a two-parter. The first step, we have to use stoichiometry to see what the theoretical amount would be. So that's the first question I'll highlight here in purple. How much lithium chloride? So this is our first step here. So I'm going to call this step 1. And so we start with what we know. We know we have 20 grams of lithium hydroxide. And so we're just using stoichiometry like we've been practicing. So we always have to go to moles. So to go from gram to moles, we're using the molar mass of lithium hydroxide, which is 23.9. And that's 23.9 grams per 1 mole. And for good practice, we are going to keep our species, so it's easier to keep track of where we are at. So now we have to go moles to moles. We're using our molar conversion. And luckily, it's 1-to-1 for everything. So we have 1 mole of lithium hydroxide. And the question is, how much lithium chloride could be made? So this is what we're converting to. And then lastly, we have to get it to a mass just by using the molar mass of lithium chloride. And so for every 1 mole of LiCl, we have 42.4 grams. This gives us a theoretical yield of 35.5 grams LiCl. So we completed step 1. Now, the second question is saying, after we do the experiment, we get 6 grams of lithium chloride. So what is the percent yield? All we have to do now for step 2 is calculate percent yield using our actual over theoretical times 100. Our actual is 6 grams. Our theoretical, we just calculated to be 35.5. And so what you get for your percent yield is 17%. And so how you properly write this is 17% yield of lithium chloride. All right. And so the next part we're going to go through is pretend like we are getting data from a lab. And so we have to know how to do this because we will be doing this for one of our labs. And so the first part gives us a word problem. Copper reacts with aqueous silver nitrate. After the reaction stopped, some copper was left over, which means the silver nitrate was used up completely. The products of the reaction are copper 2 nitrate and silver crystals. And so the first thing we have to do is write the balanced equation. And so we have copper reacting with silver nitrate. So copper is Cu. Silver nitrate, well, silver is a +1 and so is nitrate. So those just go together 1-to-1. And our products are copper 2 nitrate, which means if we have a 2+, we have to have 2 negatively charged NO3 since it is -1. And that leaves us with silver. So this is not balanced because we have 2 NO3s. So what we're going to do is throw a 2 in front of AgNO3, which means we need a 2 in front of Ag. Now we are all balanced up. Table 1. Here is the collected data from lab. And so for simplicity's sake, I'm going to label these as values A, B, and C, so I can show you guys what I'm using for each problem here. So I kind of broke down the steps. The first thing is we need to figure out what the mass of silver solid is that was made. And so what we're going to be using is equation C minus equation A. So we are taking the mass of the beaker in silver, which is 94.95 grams, and subtracting just the mass of the empty beaker, 93.80 grams. And that gives us a mass of 1.15 grams of silver. Then we have to figure out the mass of silver nitrate. And so here we are taking B minus A. Then we get 95.90 grams minus 93.80 grams. And our mass of silver nitrate used was 2.10 grams silver nitrate. So before we can figure out percent yield, it is just like the problem we did up above. We're going to have to use two steps. Step 1, theoretically seeing how much is made, and step 2, calculating the percent yield. And so in order to figure out how much theoretically is being made, we are going to take our value, our mass of AgNO3, and so we're going to convert that into a mass of silver. So don't forget that our way that we do this is if we have a mass, we have to go to moles in order to convert moles to moles and then back to our target unit of mass. Cue stuffed mole guy. All right, so let's start with that stoichiometry then. If we have 2.10 grams of silver nitrate, we need to go from grams to moles. And the way we do that is using its molar mass, which has a value of 169.9 per mole. Now, we have to use a molar conversion. And so we're converting between moles of silver nitrate to our target of just silver. And looking at the table, it is a 2-to-2 molar conversion. So I'm just grabbing the coefficients here. And then lastly, we have to go from 1 mole of Ag to grams of silver using its molar mass, which is 107.9. We end up getting, and I'm going to move this over. Oops. 1.33 grams of silver. So this is our theoretical amount. And so now, to calculate our percent yield, we need our actual over our theoretical. And so 1.15 grams is our actual over 1.33 grams. We multiply that by 100, and we get an 86.5% yield of silver. All right, so now we're going to switch gears and talk about limiting reactants. And so you may have noticed in problems the terms excess reactant or in excess. And so what it's telling you is that there's just so much of it, it won't run out. And this implies that the other reactant, which this should be fixed by the time you see it, that it will run out. And so you may encounter a problem where you're actually going to get both quantities of reactants, so they're not going to tell you which one's in excess. And this means that you need to figure out the limiting reactant before calculating percent yield. So if they don't tell you what's in excess, you don't know the limiting reactant, and so you don't know how much can actually be made. This is why this step's important. So we are figuring out the limiting reactant, which is the one that runs out first. And so my example of why this matters is, let's just say that I have 20 test tubes and 30 stoppers. So stoppers are just this little rubber thing that goes on top of the test tube. And so let's say I just want to make as many stoppered test tubes as possible. The first thing to run out, so either the test tubes or the stoppers, the first to run out is our limiting factor or our limiting reactant. Which one will it be? Will it be test tubes because we have less of them? Because we can only make 20 stoppered test tubes and then we have 10 stoppers left over. So the stoppers are in excess. And so this same idea applies to chemical reactions, except you need to compare the reactants in, I bet you guys can guess what unit, moles. And then we need to consider the reactant coefficients. And so I gave you an example here. The goofy font is because sometimes it's hard to see capital L and capital I, but it's aluminum iodide here as our product. And so we're going to determine the limiting reactant if we are given that we have 1.20 moles of aluminum and 2.40 moles of iodine. And so all we have to do here is, for each, I'm going to start with aluminum. You're going to figure out the moles of aluminum, and which we were given already. And you just have to divide by its coefficient. In this case, from the equation, it's just 2, and we get a value of 0.60. Then, for iodine, we have 2.40 moles. We're going to divide that by its coefficient of 3 and get a value of 0.80. And so all you have to do is determine which one's smaller. Well, in our case, that's going to be aluminum with the value of 0.60. So smallest, therefore, I'm going to abbreviate LR, limiting reactant. And so feel free to write that out or define that abbreviation there. So like I just said, the smallest number, that indicates the limiting reactant. So let's do another example, except here, we're not given moles. We have a value of grams, so we're going to have to do that conversion, which is super easy. Going from grams to moles, use molar mass. And so we're given aluminum sulfide, which is Al2S3, and water, H2O. So these are our two reactants. Let's see which one's the limiting reactant. So for aluminum sulfide, if we have 15 grams of Al2S3, to convert to moles, we use its molar mass of 150.3 grams for 1 mole. That gives us a mole value of 0.9980 moles. And then we are going to divide that by 1. Since there is no coefficient, it means just 1. That gives us a value of 0.09980. Then if we were to do the same for water, we have 10 grams of H2O. Its molar mass is 18 grams per 1 mole. That gives us a value of 0.556 moles. We're going to divide that by 6 because of its coefficient. That gives us 0.0927. So water actually ends up being our limiting reactant because it is smaller. So I'm writing smaller, therefore limiting reactant. And so we're going to do one more problem here. we're going to do both limiting reactants and percent yield. So limiting reactant can be just kind of an extra step because you have to first figure out what runs out, limits the reaction from producing any more product. Therefore, that's what you have to base your theoretical amount on. And so we start with limiting reactants. So we're going to be looking at copper chloride and sodium nitrate. So if we have 15 grams of copper chloride, we first go from grams to moles of copper chloride. And in 1 mole, we have 134.5 grams. That gives us 0.11 moles. And we're going to divide that by its coefficient of 1. That gives us our value of 0.11. Then we have 20 grams of sodium nitrate. Converting from grams to moles. In 1 mole, we have 85 grams, which gives us a value of 0.24 moles of NaNO3. Divide by its value of 2 from its coefficient. That gives us 0.12. So, copper chloride is our limiting reactant. Now, this gives us the value to calculate the theoretical yield. And so we always have to go, if we're looking at our reaction, we are going from copper chloride to sodium chloride. Oh, sorry, I'm just processing. I forgot to ask the second question. The second question is, what is the percent yield of sodium chloride? This will be fixed on your sheet as well. And so the second part, I'm going to write this up here. You guys already have this written down on yours though. Part 2 is percent yield if the actual sodium chloride is equal to 11.3 grams. So we are going from copper 2 chloride, our limiting reactant, over to sodium chloride. And so we've already done this first step here. So the first step of going from what would have been our grams to moles, we already did that here. So I'm just going to start with this value of 0.11 moles copper chloride. And so now to do stoichiometry to get to mass of sodium chloride, we have for every 1 mole CuCl2, there are 2 moles of sodium chloride. And then lastly, going from moles to mass, for every 1 mole sodium chloride, the molar mass is 58.5 grams. And so our theoretical is just 13 grams sodium chloride. And so to figure out our percent yield, we will take our 11.3, that's our actual, divided by our theoretical of 13, multiply it by 100, and we get 87% yield of sodium chloride. All right, so please let me know if you've had any questions during this video lecture, and I'm looking forward to checking in with you guys after you're done watching.